Okay, we'll wait for 5 more minutes to everybody come. Then I'll start. Okay. Okay, students, have you got the syllabus for your term one examination? Please respond.
Yes, ma'am.
Okay, then do you have any query regarding that, regarding the exam or something? If you have any query, just ask me. Feel free to ask me regarding the exam. Today I'll be completing the sorting, which is also in your syllabus. Then our final syllabus will be completed. And please study hard so that you can do well in your examinations.
Ma'am, like we have for data structure, we have Python and C. So
Yeah.
how will the paper divided?
See, Python and C for practical. In question paper, there are no codes will be given. Okay. No programming languages will be given. Only algorithms you have to write. So you don't have to worry about Python or C. Okay. Just follow the syllabus and what everybody has taught you in class, or I have only taught you just to with this day will it will be only 3 days, right? So previous ma'am, Bipasha ma'am, and every madam, whoever have taught you, whatever they have taught you in the class, just follow that for the theory. And in practical, the Python and C both will be there, and whatever your assignments are till date, I mean, in till previous week, that will be in your syllabus, and practice hard for that only. And maybe 2 Python programs or 2 C programs, or 1 Python 3 C programs, depending on the question. Okay, it doesn't have any particular pattern or structure. Whatever is your syllabus, just follow that.
Ma'am,
Yeah.
ma'am, for theory exam, we should practice more algorithms
Yeah,
more
you
than
have to
code.
practice the not more than codes. Codes, so you have to practice for practical anyway. Okay, and
Okay.
for theory exam, algorithms and pseudocode are important. Like you have to write down the algorithm or pseudocode. Maybe 1 or 2 functions may be given to write. Like I can give you like for stack push operation, you can write a function. So functions may be written. Total code, I don't think total code will be given to write down in a copy, because that doesn't make any sense to write down a code in a copy. So maybe algorithms are the first choice, second choice are pseudocodes, third choices are the functions, function segments. Okay.
Okay. Okay.
Okay, all the best for your exams. And today I'm going to present about merge sort and quick sort. Till now, we have studied about, first of all, bubble sort, which was not taught by me, which was taught by the previous ma'am, Vipasha ma'am. I have introduced to you selection sort, insertion sort, shell sort, radix sort, bucket sort, and what more? I don't remember. Many sorting techniques I have taught you. Just two are remaining. Actually, three are remaining. Three sortings are quick sort, mud sort, and heap sort. But for heap sort, we need to understand the structure of tree, structure of non-linear data structure. Okay. So I'm not going to teach you heap sort right now, and heap sort will not be in your syllabus. But under mud sort and quick sort, it will be in your syllabus. So I'm going to teach you right now, and now I'm going to. Okay, is this visible? Just wait. Yeah, is this visible?
Yes, ma'am.
Okay, thank you. Okay, 69 people are already there, and okay. Today we are going to talk about merge sort and quick sort. First of all, please guys note this channel link. I'm giving you this in the chat box where you can find the lectures, recorded lectures actually. Though I'll recommend you to follow my lectures as the recordings of the Google Meets are not too well. Okay. There are very much problematic recordings, more time, much time. There's no screen is recording, only voice is there. So I will recommend you to follow my class only, and please follow my class so that you can learn something. And if you cannot follow the class for a valid reason, for internet connection and all, you can go through the video lectures, recorded lectures, which will be in this channel. I cannot put the videos simultaneously after the class. I'll put it in a break, like Saturday, Sunday, I'll put all the lectures definitely. So because I have to prepare for lectures also, so I'll try to make. Okay, let's begin. First of all, till now I have I not I have we have studied about uh, the performances of the algorithms which have the complexity, time complexity of order of n square. Every time we need to conclude the worst case. Why we need to conclude the worst case? See, if you are downloading a movie, I guess everybody has downloaded a movie and know how to download a movie from torrent or somewhere like that. Whatever, whenever we are downloading a movie or a web series, whatever it is, if there is a given time that the movie will be downloaded in minimum 1 hour, is that useful? Is that something useful information we need? No. Why minimum 1 hour? We don't know the maximum bound to download the movie, so how can we sure about the time limit? So if the movie is telling the it will take minimum 1 hour and maximum 2 hours, then it is somewhat useful. Like okay, minimum 1 hour, but also it can take 1 hour, 1 hour, 1 minute, 1 hour, 2 minutes. There are several possibilities. So we don't know. We have to ultimately we have to wait until 2 hours. We cannot just we have to make time for 2 hours to download the movie. But if it is written that it will take maximum 2 hours to download the movie, then definitely it will take maximum 2 hours, and I can make a slot of 2 hours to download the movie. So this maximum scenario, This maximum concept is the worst case. Maximum how much time can be taken for a sorting algorithm to run. That is our worst case complexity. So whenever you are telling about any algorithm's worst case complexity, you are just like using the maximum term. Just think about this movie downloading scenario. Just remember this example so that you can, relate this. Just remember, whenever we are talking about worst case scenario, that is the maximum time may be taken for that algorithm in worst case. So until now, we have studied about insertion sort, bubble sort, selection sort, cell sort, and radius sort, whatever. For every sorting which are known to us, it is taking order of n square at the worst case. But what if we reduce the time complexity somehow so that it can be order of n log n? Just take any high number in a order of 2 to the power, like 2 to the power 512, 2 to the power 1024. In 2's power, take a number and just compare both of them, like order of n log n is how much and order of n squared is how much. Then you can understand that how much difference it is making. In gate examination, you have heard, I guess. In gate, these are some questions, the order of n log n, order of n square, order of n. Just compare the time complexity. We cannot, there is a way of computing all this. Just take a higher number, 2 to the power 512. For everything, every n, you have to take the same number and just calculate order of n, order of n log n, and order of n square. You can see the results, how much difference it is making from order of n square to order of n log n. That's why the scientists had invented this sorting algorithms of quick sort and merge sort. Okay, and in heap sort also, but though we are not talking about heap sort right now, will be focusing on merge sort and quick sort. So these are containing the worst case complexity of order of n log n. Okay, now merge sort is dependent on divide and conquer approach. This is an approach. See, you have to study many more approaches when you are in third year. You are doing the algorithm classes solely depending on the algorithms. There are several processes of designing an algorithm. So this is one of them. Divide and conquer. What does it mean? See, follow the name. I have always told you to follow the name. Divide the set and conquer them. Divide the set into several instances so that it will be easy to sort. If we have 100 data, isn't it obvious if we divide the data and sort them, isn't it obvious that it will be easier to sort? If we divide the data into two segments, 50 sets of 2, I know it will take a space. But that is not our concern. Our main concern is time complexity. But it will definitely reduce the time complexity. We are simultaneously computing all those subsections. That's why divide and conquer procedure for merge sort and quick sort is very, very important, which give us order of n log n in the worst case complexity for these two sorts. Now, we have to follow that how merge sort works. First of all, we need to partition, divide the list, right? How can we partition? First, one choice. If we take like insertion sort, that is also a kind of partitioning. We are just not taking extra space. In insertion sort, just remember what we have done. We were inserting from unsorted part to the sorted part. So just remember, just picturize, just visualize that. We were partitioning the array, but we were not taking any extra space. We were partitioning the array from one unsorted part to sorted part, and we were entering the element, pushing the element one by one after comparing that. But that is also a partitioning method. I agree with that. But is that efficient? That will also give us, see, that will also give us n into n minus 1 by 2 number of comparisons, which will give us order of n square in the worst case. So there's no point. So that partitioning we cannot, afford. We need to reduce that. Otherwise, what is the point of making merge sort and quick sort? If that is also giving order of n square complexity, then what's the point of making it? Insertion sort and selection sort is already there. Then we can also follow if like selection sort. What we were doing, we were also partitioning in selection sort, just the way was different. We were selecting the largest or smallest element, and we were keeping it in an sorted array. But whenever we are picking the largest or smallest element, again we have to follow n into n minus 1 comparison, which will give us order of n square. Which is the problem over here? We need to reduce the worst case complexity. So there's no point of partitioning like these two choices, taking one by one or largest or smallest, whatever it may be, the number of comparisons. Every sorting algorithm has the complexity depending on the number of comparisons. So the number of comparisons for each pass is n times for n minus 1 number of elements, one at a time. Not simultaneous comparisons are happening here. That is why order of n square is the complexity. So there's no point of using this type of partitioning. Third choice is, if we divide the whole list into two halves, then further we divide those two halves, again two halves, that will be four lists. Again we will divide them into 8 lists. Like that, we will continuing the division until there are only one element in the list. Like if there are 16 elements, first it will divide it into 8 into 8, 8 plus 8. Then it will be divided into 4, 4, 4, 4. 4 into 4, it will be 16. Then it will be divided into 2, 2, 2, 2, 8 twos. And then it will be divided into single elements. That will be 16 lists. It will take extra space, but time will be reduced. How? Whenever there is one element, there is no comparison is needed. Whenever there is two elements, simultaneously, the computer can compare the two elements boxes. There are 8 boxes of 2 elements, and I can compare them, not I, computer can compare them by calling the function recursively for each one of them simultaneously. So for each pass, the number of comparisons are reduced. For not n into n minus 1 comparisons are needed. Already they are sorted. How it is done? I'll show you in the next figure. See, we have a data set 10, 4, 6, 3, 8, 2, 5, 7. We need to divide them. First divide, then we have to merge, which is the conquer phase. First divide the array into 2 sets. How? 10, 4, 6, 3 is here. If you may arise a question, if there are not divisible by 2 numbers, then divide it like one with floor value and one with seal value. Like 11 numbers are there. One will contain 6 values and one will contain 5 values. Doesn't matter. It depends on the algorithm. If you are taking the seal value or floor value, doesn't matter. Okay, you have to divide it into 2 parts, equal parts, almost equal. One element doesn't make any change, something like that. Okay. Now, first 10, 4, 6, 3 will be there, and 8, 2, 5, 7 will be there. See, here no comparisons are done, only divisions are done. Then 10, 4 and 6, 3. It is divided. Again, 8, 2 and 5, 7. This is divided into 4 lists. Again, it will be divided into single element lists. See, everything is being divided until and unless it is being a single element over here. This is the division part. Here, no comparison is needed. Okay. Next, when we merge it, then the comparisons are needed. When we merge the elements, first we need to compare about 4 and 10. When we merge, 4 and 10 will be compared. 4, 10. No swapping is needed. 3, 6. 3, 6 will be there as it is. No comparisons are needed, but no swapping is needed. 2, 8 will be like this, and 5, 7 will be like this. Again, 4, 10 and 3, 6, we need to compare 3, the first element. Please listen to me carefully. The first element will be compared. This is already sorted. 3 and 6 is already sorted. 4 and 10 is already sorted. If, like, remember insertion sort, already less than 10? Yes. Then it will be compared with 4. Is it less than 4? Yes. Then 3 will be placed here. Then 6 will be compared with 10. Is it less than 10? Yes. Then it will be compared with 4. Then it will be placed like here. If 6 was greater than, if here, suppose 16 was here, suppose 16 was here, okay, then 16 will be compared with 10. It is greater than 10. There's no need of comparison with 4 again. Here is the tactics. Already these small arrays are sorted. That's why we don't need to compare, multiple times. That will be unnecessary. Similar thing will happen with, these two sub-arrays. First, 5 will be compared with 8. Is 5 less than 8? Yes. Then 5 will be compared with 2. Is 5 less than 2? No. So 5 will be placed here. 7 will be compared with 8. Is 7 less than 8? Yes. 7 will be compared with 2. Is 7 less than 2? No. But already we know that 5 is less than 7 because this is already sorted. So we already know there's no need of comparing with 5, 5 and 7. This is already sorted. So the place of 7 will be before 8. Here's the trick of merge sort. Again, 2 is less than 10. Yes. 2 is less than 6. Yes. Is 2 less than 4? Yes. Is 2 less than 3? Yes. 2 will be placed here. Next, the index incremented 5. Is 5 less than 10? Yes. Is 5 less than 6? Yes. Is 5 less than 4? No. Then after 4 we will place 5. As we already know this is sorted, we don't need to worry about more elements. Anything is coming after 5 must have to be greater than 5 so that it can be greater than 3 or 4 also. So the place of 5 will be after 3 and 4. Next, the index will increase. 7. Is 7 less than 10? Yes. But is 7 less than 6? No. So we can place 7 after 6 because already we know that after 7, whatever is coming, it must be greater than 7, and so it will be greater than 6 also. So we'll place 6 and 7 here. Next, 8 will be compared with 10. Is 8 less than 10? Yes. Then 8 will be, already this is placed. No need of extra comparisons will be there. So 8 will be placed and 10 will be placed. There is no element. This is the total merged elements and which are already sorted. Again, I am repeating. The simple technique, I am again repeating with the first slide. We are partitioning every array into 2 parts until and unless it is becoming single element per array. Similar, it is done here. No comparison in the divide part. We are dividing the 8 elements into 4, 4, then 4 elements into 2, 2, 2, 2, then 2 elements into 1, 1, 1, 1. We'll merge them while comparing everything. This merge is including the conquer phase. This is the divide phase. This was the divide phase, partitioning phase, and the merge is the conquer phase. That is why it is called the divide and conquer. So whenever the merge is happening, in the merge we'll compare each and every element for every sub-array. But when one sub-array is already sorted, we don't need to compare more and more multiple times. This is how merge sort works. Hope this is clear. Now we'll go to the method or the algorithm. See, one single function will be called recursively for each and every sub-array. So for each and every subarray, we'll just call the merge sort for every subarray. We'll call the left subarray, and how can we divide? We have to find a mid. See, we are finding a mid, finding out the mid. That's how we are dividing. If there is a mid, then we can divide it. Let it be even number or odd number, doesn't matter. First, we have to find the mid. Then we will. How can we find the mid? We can left plus right by 2. We can apply in just like binary search. Then we'll divide and call merge sort algorithm for every recursively for every subarray. And the sorting is just like that, comparing each element. This is how the static method is run. So this is the merge sort. Now we come to the time complexity. Remember one point, whenever this is the division n by 2 sublist for every pass, always remember the complexity will be log n for the depth of the recursion tree, and n comparisons are needed. So n for the depth of log n. How the log n came, I'll teach you in the tree class. When I will be teaching the tree structure, then you will understand why the log n is coming. For as of now, just remember one thing. For any structure, like dividing the array into 2 halves, n by 2 halves are n by 2 plus n by 2 is becoming n. Next 2 into n by 4 plus n by 4. Next 4 into n by 8 plus n by 8. Like this is how it's going. And that is why it always take to depth the recursion tree to log n. The time complexity to make this depth, this division is log n, and n number of comparisons are there. That is why the time complexity for merge sort, it will be order of n log n. And for both, all the 3 cases. Why all the 3 cases it's n log n? Just remember, there's nothing about the worst case data set or best case data set in merge sort. Everything will be divided, whatever may be the data. Let it be from ascending to descending order or descending to ascending order. It will be divided in single element. Then it will be conquered. So there's no possibility of changing the complexity by changing the order of elements. So this is how merge sort is very efficient sorting. Now we are coming to a beautiful sorting technique, which is quick sort algorithm. Very beautiful, quick sort, very quickest. But one thing I would like to tell you, this has also a drawback. Just write it down. Whenever the quick sort, how this is a drawback, I'll explain it to you. Just write down as of now in your note copy. This is a very important MCQ also. For the ordered list, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this, already sorted in ascending order. This will occur in quick sort. It will take order of n square of complexity. Why it will take it? I'll explain it now. Okay. Now first, what we have to do in quick sort, we have to take a pivot element. Whichever element you want to take as pivot, you may take. We can divide the array into 2 subarrays. Like one subarray will contain the elements which are less than pivot. One subarray will contain the elements which are greater than pivot. So let's go to the example so that you can understand. First of all, these are the set of elements 40, 20, 10, 80, 60, 50, 7, 30 and 100. First, let's take 40 as the pivot element. You may take whatever you want, doesn't matter. If you take a value which is, is a median or, median is a term basically. If we consider all the elements, then 40 is the median of this particular set of the elements. That's why I am taking 40. There's no hard and fast rule to take pivot element, whatever it may be. If it's your choice, nothing is a problem. So we are taking 40. as a pivot element. Next, what we are doing is the given pivot element, what I have told you earlier, that one subarray will contain the left side which will be less than the pivot element, the elements who are less than the pivot element, the elements who are greater than the pivot element. So this is how the divide part will go on. How? See, first we have the pivot element 40. Hope this is visible. If not, then please tell me. This is 40 pivot element, the red one. The leftmost part, other than the pivot element, is the too big index, and the rightmost is too small index. First, while data of too big index means the 20. If 20 is less than equals to data of pivot, data of too big index is less than equals to data of pivot. So what is the data of too big index? That is 20. What is the data of pivot? That is 40. If 20 less than equals to 40, obviously, then plus plus too big index. Index is incremented. See, index is incremented. It was 20, 10, 80. I hope this is visible. If too big index, again, we are comparing the data of pivot. Obviously, it is greater, data of pivot is greater, then we will increment the index. Now, it is not greater. 80 is not less than equals to 40. Now, what we have to do? Step 2. This is this is the, algorithm you can write it on your paper also. If someone asks you to write down the quicksort algorithm, you can write it, okay? While the data of too small index, now we are moving to too small index, this one is greater than data pivot. Yeah, it is greater. We are decrementing the index. Previously it was
Yeah,
100,
Medashri
it is now,
madam. Hello,
yeah.
Medashri madam.
Hello.
Hello. Yeah,
Yes,
Medashri
yes.
madam. This is
Yes,
SKG here. Hello. Hello.
sir. I am listening to you. Yes.
Can you please mute yourselves? I am listening echo from my side. Yeah. So, Honorable Vice Chancellor sir is attempting to get into your class. So please allow him. Right? Please allow him. Vice Chancellor sir is trying to get into your class. He got denied once. So please allow him. Thank you.
Just wait, students. Bipasha ma'am, can I continue teaching? Just wait for 5 minutes, students.
Hello, Ministry. Hello, Ministry.
Yes, ma'am. Yes,
Okay,
ma'am.
has Minister joined?
Okay, should I continue?
Yes, yes, you continue. Actually, we have called you that.
Okay, my phone was in silent mode. That is why. Sorry, ma'am.
Okay, fine.
Okay, thank you. Okay, just follow me, student. First, you have to, ma'am. Could you please mute, ma'am? Okay. First of all, we need to focus on the data of pivot. The data of pivot is 40. First one is while the data of two big index is less than equals to data of pivot. Now what we have to do is the data of two big index is 40. The data of the data of two big index is 20 and the data of pivot is 40. We need to compare those. Is the data of two big index is less than equals to data of pivot? It is yes. Then we are incrementing the index of two big index. See, we are incrementing. Previously it was 1. Now it has become 2. Now again, this is a while loop. We need to follow this until and unless the condition is failing. So we need to increment it. We have incremented. Again, we have to follow the same loop. The data of two big index is less than equals to data of pivot. See, 10 is less than equals to 40. So we need to increment it again. Now, previously it was 10 and now it is 80. The index is incremented. Just don't get confused. The index it is which is incremented. And we are comparing between the data. The indexes are containing. Now it is containing 80. So is 80 less than equals to 40? No. The while loop breaks. Now we'll go to the second instruction. What we have to do for the second instruction is we need to focus on two small index. Two small index is 100 here. Here it is 100. We need to see that while, again it is a loop, while the data of two small index, again we are comparing among the data, not the index. Please focus, we are comparing the data, incrementing and decrementing the indexes. Two small index is greater than data of pivot. 100 is greater than 40. Is this true? It's true. Then we will decrement the two small index. Decrementing the index, previously it was 8, now it is 7. Now it is becoming 30. See, this was 30. Now this is 30. Again, we have to follow the while loop until and unless this breaks. So is 30 greater than data of pivot, which is 40? No. That means this will break. Next point. If two big index, now we are comparing the indexes. Please focus. Now we are comparing the indexes. If two big index is less than two small index, then we have to swap the data between two big index and two small index. We are swapping 30 and 80. Again, I'm telling you from beginning. First, what we have done, first, while loop is running, data of two big index is less than equals to data of pivot, which is 20 and 40. 20 is less than equals to 40. True. We are incrementing the index to 2. Now it is 10 and 40. 10 is less than equals to 40. True. We are incrementing the index. 80 and 40. Is 80 less than equals to data of pivot, which is 40? No. Then we'll go to step 2. While data of two small index, which is 100, is 100 greater than equals to 40? Sorry, greater than 40? Yes, we'll decrement it. Is 30 greater than 40? No, we'll go to step 3, while loop breaks. Now we'll compare the indexes. If the data of two big index is, not the data, the index, the two big index is small then smaller than 2 small index, which is 3 and 7 index numbers. Focus on the index numbers. We'll swap the data. We'll focus on the index numbers. Is 2 big index smaller than 2 small index? Is 3 is smaller than 7? Yes, we'll swap the data. See, now 30 and 80 has been swapped. Now what we have to do? While 2 small index is greater than 2 big index. Now 2 small index is 7 and 2 big index is 3 is greater than, that means 7 is greater than 3. Go to 1. We have to repeat this. Again, we have to check. From step 1, what we have to do? While loop is running. Just be with me. If you have any problem, please ask me. Do interrupt me. I won't mind. While data of 2 big index is less than equals to data of pivot. Again, we are following the same process. What is the data of 2 big index? That is 30. So is 30 less than equals to 40? Yes. So what we'll do? We'll increment the 2 big index. Incremented. Now it is 60. Now while loop breaks. 60 is not less than equals to 40. What we have to do? We'll go to the second step. While data of 2 small index, which is now 80, is greater than data of pivot. True. We'll decrement it. Now, this is 7. This is where the second while loop also breaks. The condition breaks. Why? This is 7. 7 is not greater than 40. So, we'll stop and go to step 3. If 2 big index is smaller than 2 small index. Now, we are comparing the indexes. Again, 2 big index is 4 and 2 small index is 6. If 4 is less than 6, then swap the data of 2 big index and 2 small index. Which will be swapped? 60 and 7 will be swapped. These two. See, swapped. Now, again, we have to go to while loop of 4. While 2 small index is greater than 2 big index, go to 1. 2 small index is now 6 and 2 big index is 4. Is it greater? 6 is greater than 4. So, we will go to step 1 again. Now, again, we have to compare 7 with 40. While the data of 2 big index is less than data of pivot, is 7 less than 40? Is 7 less than 40? Yes, it is less than 40. Then we'll increment the 2 big index. It is 50. Now this while loop again breaks. Condition fails. We'll go to step 2. We'll check the 2 small index. 2 small index is 60. 2 small index data is greater than data of pivot. 40 is greater than 60. We'll decrement it. Again, here 50 is greater than 40. 2 small index is in 5. Here, see, don't get confused. Here, 2 small index is working. Already 2 big index was here and 2 small index is working. It doesn't matter if both of them are in same position. It doesn't really matter. If 2 small index is greater than of data of pivot, the data of 2 small index is 50 and the data of pivot is 40. So, we'll just decrement it. Now the condition fails. The data of 2 small index is 7 and the data of pivot is 40. This while loop condition fails. Then we'll go to step 3. If 2 big index is less than 2 small index, now we'll check the indexes. 2 big index is 5 and 2 small index is 4. No, this is not happening. So no swapping will be done. Now we'll check while 2 small index is greater than 2 big index. 2 small index is 4, 2 big index is 5. No, it is also failing. Then we'll go swap the data of 2 small index and the data of pivot index. What we'll do? Just follow me. Swap the data of 2 small index, which is 7, and the data of pivot, that is 0, which is 40. Data of pivot is 40. 0 is the index number. We'll swap it. See, pivot is coming in the middle place. Now, this is how the divide part will happen. Now, what I have told you earlier in the previous slide, I'll go back to the previous slide. Just wait so that you can recapitulate what I have told you in the first place. See, the partitioning will contain one subarray that contains the elements which are greater than equals to pivot, and another subarray that will contain the elements less than pivot. So this is how this is happening. This is the whole procedure, and we have to call the function recursively for this subarray and this subarray. The array has been partitioned into two parts. The same function, this function, will be called recursively for each and every subarray. This is how the quick sort is being done. Now, whenever the partition has been completed, we'll just call it the merge function will merge the arrays. There's no need of comparing anymore, as other than merge sort, not like the merge sort, it is already been sorted by using the too big index and too small index. So this is how the quick sort is done with the subarrays, recursion of quick sort. You can write the algorithm which I have shown in the PPT as your answer of quick sort algorithm. Now the time complexity. Any algorithm we are focusing on, we need to focus on the time complexity. As I have told you earlier, in the merge sort, the quick sort is also dividing the array into two subarrays, and preferably the subarrays are partitioned into two halves. So the running time for quick sort analysis is also order of n log n. The worst case, remember, the worst case complexity is order of n log n. So now I guess you have followed the recursion tree in the merge sort. In the merge sort, what we were doing? In the merge sort, we were just dividing the elements into n by 2 halves until and unless it was becoming one element per subarray. Similarly, the quick sort analysis is doing the same, just taking one element as a pivot. That is why whenever we are doing this division algorithm, this divide and conquer process, the complexity will be order of n log n. Now let's move on.
Bega, please keep your video on.
Sir, I have recording this.
Can you keep your video on so that I can see you? Okay, slide more.
Visible, sir?
Yes, please. Thank you. Thank you.
Welcome. Now, this is the complexity analysis for quick sort. Now I'll go to the best. Like the median of the element, as the array is a homogeneous collection of data. If we choose the element median of all those elements, then it will be easier for us to divide the array into two equal parts. So the key element for quick sort is just how you choose the pivot element, so that you can find your algorithm properly. So this is how quick sort is done, merge sort is done. Hope you guys have understood this. So I am just my sharing option right now. I'll be giving you the quiz link. If you have any question, please do ask me. If there is any question, please ask me. I hope there's no question anymore. Students, please ask me if there is any question. So I am assuming that you have understood what I have taught you today. I am giving you the quiz link in the chat box. I'll be giving you this slide to your Telegram group, which is containing my channel link also. You can subscribe the channel so that you can follow the lectures when I am not available online. And those who have missed these lectures can also follow that if they want to follow for a valid reason. Please do follow. All the best for your exams. And I am here. You can ask me anything regarding exams, regarding this study, regarding what I have taught today, anything.
Ma'am, is there any formal procedure for writing algorithms? Like we have to say that the start of the loop and then the end of the loop or anything of that sort?
See, algorithms doesn't have any formal hard and fast rule, but pseudocode have. If you are asked to write the pseudocode, then you have to follow the rules like while, for, the incrementing, the decrementing. You have to follow everything. But if you are asked to write an algorithm, it is, it is a good approach to write an algorithm just like the pseudocode only. If you write only the steps like we are doing such and such in the statements, that is not a good approach to write an algorithm. That is not desirable. Though I am telling you that there is no hard and fast rules written anywhere to write an algorithm. There are rules for pseudocode, but what you have to do is you have to follow a approach because you are computer science student, isn't it? So you have to follow the while loop. You don't have to write the codes or taking the integer variable, int I, int a, not like that. Explicitly you don't have to write code, but follow the loops. While, for, follow the loops, the incrementing, the decrementing. Try to write as I have shown you in this lecture. Try to write that way. It is very much more appreciable. Is it clear,
Okay,
Orkoji?
ma'am. Thank you, ma'am.
Welcome.
Ma'am, if we write as step 1, step 2, it won't be granted.
See, it won't be grant. That is a very big statement for me to tell. It is it. It is not like that. It won't be granted. It is depending on the examiner, whoever is checking your copy. Like if I am checking, I'll be asking for you to be a little more scientific. Not like this is not a theory, right? This is computer science. So you have to be scientific. So if you are understanding the algorithm, if you are understanding the approach, see whatever I have taught you today, everything is steps. Everything is a step. It is written in step, but it is written in a scientific approach. Try to follow that approach only. I am asking you to try to follow that approach, nothing else. And it is not hard. Try to understand the concept. It is not hard to write down a loop. What does a for loop do? It is just keep repeating a step, isn't it? So is it very tough to follow a scientific approach? Don't get afraid of writing algorithm in a codal form or any, incremented, decremented form. Don't be afraid of that. It's very easy to write if you have the concept. Is it clear? Yeah, Bhattacharya, is it clear?
Yes, ma'am.
Thank you. Anything else? Sorry, my internet connection got lost.